Welcome, everybody, to the first official Isaac Lab office hours. So excited. As you may recall, if you watched the live stream last week, we covered Isaac Lab, going over some of the features and benefits. And today we're going to continue that along with taking your questions live. So if you're tuning in from whether it's X or LinkedIn or YouTube or Twitch, feel free to go ahead and join us in the chat and ask your question or post your comment. Let us know where you're watching from. That's always fun to see where people are calling in from. And we, as you can see, we have our very special guests here with us. Let's go around and start introductions. Asari, we'll start with you.
Yep. Hello, everyone, and thanks for joining. My name is Asaveri, and I'm a technical marketing engineer, a TME here at NVIDIA. I work very closely with some of our Isaac platforms for robotics. So maybe you've heard of, or maybe you've even used Isaac Sim before, our simulation platform, Isaac ROS for robotics, and of course, Isaac Lab, which is the focus of today's live stream. So I'm just going to be talking here a little bit about Isaac Lab, some of the features, functionalities, things you can do. And then we also have Oyinda Mola with us, who's going to be taking us even more into some of the more technical detail about the workflows. Over to you.
Amazing. Thank you. Okay, Oyinda Mola, do you want to introduce yourself, a little bit about your background?
Okay. Hi, everyone. My name is Oyinda Mola Omotuyi. I'm the technical marketing manager at NVIDIA. Actually, technical marketing engineer at NVIDIA for most of our Isaac Lab platforms, or our Isaac platforms. So majorly on Isaac Lab. So today I'll be working with Asari to be able to work with everyone understanding Isaac Lab workflows. How do I get started with Isaac Lab? How do I build my examples end to end? So that's what we're going to be doing here. Thank you.
Amazing. It's great. And I have to say, we had a ton of viewers, both live and afterwards. So if you missed the beginning of this or you want to watch it again, these videos live on our YouTube channel. You just got to go to the NVIDIA Omniverse YouTube channel and then go to the live section, and you'll see all of our previous live streams, including this one, which will be available following our airing date right after this concludes. So we have some great people coming in. I see hello from Portugal, from Ghana, from Italy, San Antonio, of course, Brazil. So we have a global audience here. Let's actually talk about something really quick and just clarify that Isaac Lab is the successor to Isaac Gym, correct? So in case people are familiar with Isaac Gym from previously?
Yes.
Okay, great. All right. So anyone who needs clarification on that, feel free to talk to us afterwards. And of course, we're going to take your questions live as we go through this initial presentation. And so I'm going to let you guys take it away. You have this great slide up on the screen.
Awesome. Thanks, Edmar. So yes, for everyone who's joined last Wednesday, we had another one of these, I believe. Feel free to start putting your questions in the chat. And what we're going to do is try answering them in the chat, but then also like verbally answering some of them. So we'll keep pausing maybe every 5 or 10 minutes, and we'll try to have like a more interactive open discussion. So feel free to ask follow-ups as well. And for more complex questions, like maybe things where we need more details from you, or we need to understand your setup and log files and stuff like that, we'll also be sharing a link to the forum or the discussions on GitHub where you can keep posting some of those kind of questions as well. So let's start off with today's agenda. We're going to do a very quick overview about what the features are for Isaac Lab, how you can use it, and what use cases it can satisfy. We'll also just be talking about some basic requirements you need to set up and get started to use Isaac Lab. And then we're going to be going on to a little more technical detail. So that's where the reference architecture, the data flow, and sim-to-real workflow comes into the picture. Through those sections, we're going to be understanding how you can really start using it for your particular use case and customize it for what you want to do. So let me talk a little bit real quick about the entire ecosystem, how Isaac Lab works with Isaac Sim and NVIDIA Omniverse. Let's start from the bottom up. So NVIDIA Omniverse is a huge platform. It's a large collection of, you have libraries, different SDKs and APIs to build 3D assets and robots in simulation. So it is for more than just robotics use cases, but of course today we'll be talking about in the context of robot learning. So with NVIDIA Omniverse, you have a physics engine that does physics-based simulation for all use cases. And then you have very realistic photorealistic rendering. So in especially visual use cases where you want to get as realistic a simulation as you can, all of these things are enabled by Omniverse, which is kind of the biggest bottom of the platform over here. All of this is enabled through USD, OpenUSD. So that stands for Universal Scene Description. People who've used Sim before may have heard of this concept. It's how you describe assets and robots and like 3D interactions among different objects. So built on top of Omniverse, you have NVIDIA Isaac Sim, which is the simulation platform. And this again gives you a whole new set of functionalities. So one of them is called OmniGraph, and that is for visual scripting, which kind of means that even if you don't really want to code in Python or anything, you can just use the GUI and develop applications and test your use cases from there. So that's a bit about OmniGraph. And then for the robotics platform, you have ROS, which is a very popular framework it stands for Robot Operating System, ROS. It's not an OS, but it's a protocol. It's a communication system for communicating between different robots. That is also something that Isaac Sim enables through the ROS bridge. We have extensions for that as well. And then you have the importer for different kind of robot assets. So if you've already used URDF before or MuJoCo before, another popular physics engine, you can import all those robots and assets into Isaac Sim and start using that. And now finally, we go to the top of the pyramid, which is NVIDIA Isaac Lab, built on top of Isaac Sim. And Isaac Lab is intended to be an extremely lightweight extension. So it pulls all the useful functionalities from what we discussed, like Omniverse and Isaac Sim below it. And then it gives you a very focused tool to build robot learning applications. So whether you want to use or implement reinforcement learning or imitation learning, these are some concepts we spoke about previously, and we'll be touching upon them throughout this the office hours as well. All of these things are enabled from the Isaac Lab layer. And we'll be, as we go forward, we'll see how to do specific things as well. Of course, we may not cover everything in this particular office hours, but this is meant to be a recurring session. So we'll keep learning as we go forward in each. So let's move on to the next slide. Let's talk a little bit about the robots that are already available that exist in Isaac Lab, in which you can kind of just plug and play and start using them. So we have over 16, 18 different types of robots. Real quick, let me describe some of them. So some of them are your basic robots, which are like a cart pole. Imagine just like a cart with a pole on top of it, but you can start, those are very good robots to start learning and understanding how to use the platforms themselves. And then you have for dexterous manipulation use cases, maybe you want to do like a pick or place application. So over there you have fixed arm and a robot manipulator. That's the second kind of robot. You have quadrupeds. So quadrupeds are kind of those cute dog-shaped four-legged robots. We have the animal Spot from Boston Dynamics, the Unitary, Go 1 and Go 2. All of these are different types of four-legged robots, which you can test different kind of, we'll also in a moment be looking at the different use cases or tasks that you can train these robots on. Coming to more complex forms, there's the humanoids. Those are especially getting popular now with like, we have the Unitary asset and I believe a couple of others as well. And then 1 or 2 examples of quadcopters, which is like the aerial robots. And then you can also import some of your own through URDF and USD. So that's the idea, that this is meant to be the platform using which people like developers like yourself should be able to import your own and customize your own robots. And now let's take a minute to look at the sensors on the right of the slide here. When it comes to sensors, again, all of these are already available in Isaac Sim. So for users of Isaac Sim, you're quite familiar, I'm sure, with the different cameras we have, and also the tactile sensors, contact sensors. As your robots get more and more complex, like when we move to humanoid use cases, for example, you might be using a combination of any or all of these different sensors. And so a lot of them are already like pre-existing and modeled for you in Isaac Lab, which you can then use in Isaac Sim, which you can use in Isaac Lab as well. So let's move on real quick and take a look at some of the available environments. So an environment is really nothing but sort of like the interface between the robot you want to train or the robot on which you want to implement any of these algorithms and the simulation itself. So Isaac Sim. So some examples, I think it's best understood through an example, would be dexterous manipulation. So when you want to, say, have a bunch of objects on the table and you want to train your robot arm to pick them and put them in a box or something, that's one type of environment Isaac Lab provides. And then you have locomotion, which is basic walking. But of course, it's not as easy as it sounds. Even to train a robot or like a quadruped to walk, you have to take into consideration the different type of terrains. So you'd probably train a different model or policy for like a flat ground versus up the stairs. So all of these different kind of environments and terrains are something that is provided already. You have functionality from multi-agent RL. So I'm not sure if the image is super clear there on the top right, but if you have, let's say, two robot arms that want to interact with each other, pass a ball between them or something, that is where you're actually training for multiple agents or multiple robots. And then, of course, you have navigation for like giving an end position, and the robot will navigate from current pose to the end pose while avoiding obstacles or not. These are all different things you can do using Isaac Lab. Of course, the algorithms you implement may be something that you have to test and try, but that's exactly what this platform is for. Then you have tiled rendering, which is a very interesting feature of Isaac Lab, and we're going to get more into it in a minute. But essentially, it's meant for visual RL. So where you want to implement a camera-based setup, like a camera looking at the scene or looking from the point of view of a robot, perhaps, tiled rendering is a feature that lets you do that. And then you have teleoperation, imitation learning. So imitation learning is learning through demonstration. So you have like a teacher or a demonstrator, like a human, let's say, for a humanoid. And this person will be doing different actions, which can be recorded as data that can be used to train a humanoid to do the same thing. So this is a very data-intensive process. But then again, Isaac Lab is something that enables you to collect that kind of data and to replicate it as well. So that was a quick look at some of the environments. I said we'll talk about tiled rendering, which is a particularly interesting, a key feature. So imagine you want to train many scenes with from the point of view of a camera in simulation, right? Now you can imagine that, say you have 1,000 cameras, each camera rendering an image means 1,000 images. And that is going to be very compute intensive and quite slow as well, right? And not everyone has access to like the beefiest of GPUs. So the idea of tiled rendering is to solve that issue, wherein instead of rendering 1,000 images, you actually kind of almost concatenate them into one big image. But rendering that one big image is actually more compute effective or efficient than rendering 1,000 images. So that's the idea of tiled rendering, literally just concatenating into one big image and render that big image. So you save a little bit on compute. This is especially useful, not in a standard, you may not be using it for like a standard reinforcement learning policy for, let's say, locomotion. But when it comes to doing more complex tasks where you have to maybe see objects in the environment and interact with objects visually, that's where this feature becomes especially, it's especially important to reduce the compute that you need in that case. So at this point, I do see many questions in the chat. So maybe we can take a minute and try answering some of these, and then we'll just move real quick onto how to get started.
That sounds great.
Yeah.
Do you want to read any of them, or do you want me to click on some as I scroll through them?
Sure. I'm trying to see if any of them are easy to answer right now. Oh, I see one. Here, let me try.
Yeah. Okay, you can go ahead, Asa.
Gotcha. Hi, I am curious to learn the key differences between Isaac Lab and Gazebo. I'll answer a little bit about what I know. Oyindamola, feel free to chime in whenever. So the difference would be that Isaac Lab is tuned for, rather it equips you with everything you need for robot learning. So reinforcement learning and imitation learning specifically. Of course, Gazebo is a very good physics engine and simulator. It's, the popular choice for when you want to start simulating initially. But I feel like the features that Isaac Lab gives, especially tiled rendering being one of them, and like multi-GPU, in parallel, you can scale up environments and train. That is something that's kind of unique to Isaac Lab, and that it tries making the scaling up part much easier. Oyindamola?
Yeah, definitely. So another thing also is, I think with the last live stream we talked about the three key pieces of robot learning, which is the next slide we're going to talk about. So Gazebo is a robotic simulator, and it's when it comes to robot learning in NVIDIA ecosystem, that would be Isaac Sim. So Isaac Lab is based on Isaac Sim for robot learning. So I wouldn't say different between Gazebo and Isaac Lab. I'll say different between Gazebo and Isaac Sim, which is what Asawari has answered. Yeah, thank you. I think we can go to another question.
Yep. I've pulled
Okay.
one up here.
All right.
Let me read it out. Is there an initial example to try Isaac Lab with Isaac Sim as a tutorial? And it also shows you step by step the installation of both. Excellent question. That's coming up. If so, where can I find it to try it? Okay, just hold on for a minute. We're going to be sharing the links in the slides and also in the chat as well. It'll show you both installation and several tutorials. Actually, we have like 10, 15 plus tutorials, I think, on getting started with Isaac Lab. So we'll share a link to that in a minute. Let's do one last question before moving on. If you may please mention how to connect a remote headless machine installed on a workstation from a local machine. Good question. I think this is easiest answered with a link, which I'll share in the chat. But the Isaac Sim documentation gives, maybe the Isaac Lab documentation as well, it gives a couple of options on how to doing exactly this. So you can be running Isaac Sim on a machine with a GPU somewhere, and you can use WebRTC or some other protocols to just connect to it. You can also use some open tools like No Machine and stuff. I'll maybe link to a couple of these examples in the chat, David, so you can check out those ideas.
Okay.
Okay, thank you all for your questions. There are many more. We'll get to those in a minute or in the chat. But let's move on real quick with how to get started. So first of all, let's understand the three parts or the three key pieces of robot learning and how like you can use the entire pipeline together. So the first is that of a data generator or a simulator where you can create the data that you want to actually learn in the real world. So the idea here is that, of course, it's not possible to set up different scenarios for your robots to learn different things in the real world. That's very expensive and time consuming. You want to do this ideally in simulation where it can be much, much faster and you can do different types of data generation, like more diversity in your data set as well, right? So for all of that, the first part, which is that of Isaac Sim, the simulation platform, which is your data generator and renderer. So that's the first part. Then you have the second part, which is a way to use these environments or the data set generated to build environments for reinforcement learning. So just having the environment or having a rendered environment isn't enough. But when it comes to reinforcement learning, there are concepts around reward functions and observations coming from the environment, and that then the actions that the robot takes and how that affects the environment. So all of these functions and concepts that come within reinforcement learning need an interface with the simulation. And that's the second part of the piece, which is Isaac Lab. And then finally, you have the third part, which is the actual implementation of all these reinforcement learning algorithms. So there already exists a bunch of popular frameworks that Isaac Lab tries to support already. A couple of examples, maybe you've worked with these before, but a couple of examples are Stable Baselines 3, RSLRL, RoboMimic. I believe Isaac Lab is compatible with 4 or more different reinforcement learning libraries. And the beauty is that you can bring your own as well. So if you have your own custom algorithm or your custom library for learning, you can write a wrapper for it and make it interact through or with Isaac Lab. So even for all the supported libraries, there are wrappers that allow you to convert data format and use the same data types between Isaac Lab and these different learning libraries. So these are the three key pieces and how they work together. Essentially, imagine Isaac Lab is in the middle, and then you have two things feeding into it. One is the environment in simulation coming from Isaac Sim. That's one thing feeding into it. And then the second is the reinforcement or the robot learning library itself. Currently, there are 4 or more supported, but of course, you can bring your own as well. Finally, this is a table. You will also see this on the Isaac Sim documentation. The reason is that Isaac Lab is built on top of Isaac Sim. So all the compute requirements that you use for Isaac Sim, if you already have Sim working, that's great. That just means Isaac Lab will work as is. Of course, you just want to check some of the versions and make sure everything is compatible. But this table is something we'll share with you, and it's also on the public documentation. So just make sure that you have, if not the ideal requirements in the farthest right column, at least something that's good to run Isaac Sim. And with all of this, you should be able to move on to the installation and setting it up. So that's this slide to answer the question we got previously. The first two links here are just about installation guides, how to install Isaac Sim and then Isaac Lab on top of that. And then you can follow the several tutorials. There are a bunch of tutorials for different things, like how to set up a very basic scene, how to bring in your robot, make them interact. So the best suggestion would be to follow those tutorials one by one in that flow that it's given on the documentation. And then the Isaac Lab reference architecture is something that we're going to be speaking soon. It's coming up right now. But it's a high level understanding of all the different components that work together, because it is a lot of pieces, of course, but what each piece means and how you can use it to do whatever your use case requires. So these important links, I'll make sure to share them in the chat as well. And then once we share these slides, you can refer to them straight from here. Down here, we also have a couple of examples of real world use cases, like companies actually using Isaac Lab to do different tasks, either for humanoids or for manipulators, both. So those are very interesting stories. And there are some blogs around those as well, which you might want to read. And at the very bottom, we've linked to a couple of blogs. One of these, I believe the last one is just an introductory, like what is Isaac Lab kind of a blog. And then the one on project GR00T, that's the one that's, it's kind of a collection of foundation models to build humanoids and different kinds of robots. And a lot of these components use Isaac Lab. So they've been trained to do different tasks. Of course, one task might be a robot arm or manipulator. So that would be one task. Another would be whole body control for a humanoid. Another would be the perception part of it. A lot of these parts have already been trained using Isaac Lab. So that's another good way to get started. And finally, we have a blog on the Spot robot, quadruped from Boston Dynamics. That's the blog that shows you how to do the entire pipeline. So from simulation to real world deployment. So what happens there is that you take the Spot robot in Isaac Sim and in Isaac Lab, you train it for a locomotion policy so that it can walk on a flat terrain or even a rough terrain, I believe. And then you just deploy that onto a Jetson, onto a physical Spot robot. So that shows the whole story end to end. Pretty interesting blog. I'd encourage you guys to read that.
Okay.
Yeah, so I think we could maybe take a couple of more questions, maybe 2 or 3, and then on to Oyendamola for talking more about the reference architecture.
Okay. Thank you so much, Asa.
Yeah.
I think there are some few questions we could just really talk about real quick.
Yeah.
I think one question is about any environmental examples that can be planned for drones, multi drones in Isaac Sim Isaac Lab environment. Okay, we currently have one environment for drone. That's the UAV for it to be able to navigate or over to a particular point. So that is one example that we provide. And of course, multi-agent environments that we're creating for other kind of robot that can be used, replicated for multi-drone systems. I think that answers that question. Okay, do you see any question that we could quickly?
Yeah, I'm taking a quick look. There's a question that says works with ROS2 and ROS1 both. I'm assuming this question means whether Isaac Sim or Isaac Lab works with both. The answer is yes. Isaac Sim has an extension for ROS. It's called the ROS bridge for ROS1 and ROS2 bridge for ROS2. And so after you enable whichever one you want, you can use it with either.
Yes, exactly. So one of the things also you can do is to take your train policy in Isaac Lab and then open up Isaac Sim and use that train policy connected with ROS bridge to be able to use your train policy with ROS. I think that is on Isaac Sim documentation. Yeah, let me see.
I think I see one. Hold on. One last question maybe before we move on. Is the physics engine used in Isaac Lab Physics 5 or can other engines be used?
Okay, so yes, the physics engine we use is physics, and other physics engine, there are definitely different collaborations that's going to be happening in the next couple of releases that enables us to be able to use multi-physics for Isaac Lab. So let's watch out for that, and I know that will be very exciting for many developers that have used other physics engine. So that's really good. Okay, so we're going to go straight into Isaac Lab reference architecture or data flow. And I'll just try to take it step by step. And this is basically what we call the deep dive into the Isaac Lab workflow. The question I want to answer is that I have an example. How do I get started with Isaac Lab? How do I get coding? How do I get, doing all of those examples that we'll see? So for us to be able to do this well, I'm going to start with an example that we have already in Isaac Lab. I'm just going to walk through how it was designed from the initial points to actually deployment. And also, this is a very, I won't say basic example because it's not basic, but it's basic enough for most people that don't want to just work with catpole. This is animal robot. This is a quadruped, four-legged robot. And the goal here, we're trying to train the robot to be able to walk on a flat terrain. And for you to be able to train for any robot learning system, one of the first things that you care about is the observation space. Like, what are the inputs to your neural network or your policy for you to be able to train a robot to walk? And that's what we call observation space. So for instance, for a quadruped, you have the base and also the joint. So you have the base velocity, both for positional velocity or angular velocity. You have the gravity. You have also since we're trying to train it to walk in a flat terrain, it means that we're giving it target X, Y, and your velocity. That's the forward velocity, the X, Y, and also the rotational velocity. So that is included in the observation space. Also, the degree of freedom states, that's the joint state, both for position and velocity. One of the interesting part in where you design your observation space for a quadruped that is walking is to take the last action it took and then put it back into the policy and then use that to train. Of course, the initial action is going to be zeros because you've not taken any action, and then a combination of that can form an observation space. Of course, it's good to note that you could include like a vision sensor or vision reading camera images, like using the tire rendering feature that we have in Isaac Lab, the LiDAR rendering based on the complexity of the task. So for instance, if you're doing things that involve like obstacle avoidance or walking through navigating through a particular area, you might want to add more complex observation for that. The next thing you care about is what is the output of your policy? The output of your policy will definitely be the joint state, which is the 12 degree of freedom joint position for you to be able to control the robot. For two ways to be able to do this particular task will be number one, to follow the imitation learning path or the reinforcement learning path. Now, the imitation learning path, you can drive the robot around, you can get information or the position or like drive the robot around and get the data for it and then train the robot to be able to do that. Or you go through reinforcement learning, which require you to be able to design a reward function. So in this case, we have the reward function. Since we're trying to track the linear velocity and the angular velocity, that will be definitely the first thing that I want to put in our reward function. And we have a linear velocity penalty, angular velocity, joint motion. So this reward function is something you define, but we are definitely giving an example right here. And this is already put in the Isaac Sim technical paper or Isaac Orbit technical paper that you can actually see this. The next thing we want to look at is how do you define your environment step? So you pass an action in environment and then the robot perform that action and then you get the next state. So that would definitely require you to design some functions like the physics step, the reset function, the termination. How do you know that the task is done, or how many episodes do you have to run for you to end the task, something like that, and then randomization. So this is a very simple example for us to be able to walk through how do we do something like this in Isaac Lab. I believe that all of us are excited to follow me through this. And I really hope it's not going to be too much information at once. So let's just try to work this together. It would be nice to see. I wish there's a way to see faces, but it's not possible. But it's okay. We could work with just comments so that we can know you're following us. All right. So the first thing in Isaac Lab is your asset. The first thing you need is an input to your asset. So the first step to training with Isaac Lab is to have the USD file of your asset. So when we're talking about our asset here, for instance, the example we're looking at, the three assets that we're looking at is the robot, the ground plane, because the robot needs to be on the ground. If not, it's going to fall through the ground. It's going to fall through the air, so to speak. The lightning, just from some aesthetics, right there. The sensor. In this case, you are using like a contact sensor because the robot needs to touch the ground. How do we know it touched the ground? The contact sensors and all. So also another asset you need definitely is your robot, and that can be in USD, URDF, or MuJoCo file extension. So those are three that we support. But and if you want to do this, the first thing you can do is to design your asset or your robot in Isaac Sim and export it in USD file, or you design your robot or asset in any of the CAD software and export it to USD using any of the Isaac Sim converters. So we have card converters, we have other kind of converters that are right there in Isaac Sim for you to be able to convert from your own extension like .obj, to USD, and then that can then be used in IceClub. So IceClub provide wrappers over MJ, CF, URDF importers in Isaac Sim for you to be able to allow you to define your robot in a format that can be loaded directly into IceClub. And then, of course, in some special cases, you might need to add like things like slight modification, like physics or closed loop kinematics, to your imported asset. So when you have your asset, so when I mean you have your asset, meaning you have the file of your asset. So say animal.usd, that file of your asset. Now, for you to be able to now spawn that asset into Isaac Lab, we do that using what we call asset or scene configuration. So for each individual asset, robot, sensor, ground plane, lighting, each and all of them have their own individual configuration. So Isaac Lab uses what we call asset configuration classes to be able to spawn this object into the scene using Python. So the next step for you is you have the file.usd. The next thing is to write your configuration class for it. Now we already have different robot already in Isaac Lab, different assets. We have lightning, we have ground plane, we have some cubes, we have some objects that is already predefined in Isaac Lab that you can just import their configuration classes. But then if you want to write your whole new configuration class, we already have that in the documentation. So documentation had a section called resources tutorials, and in the tutorial, one of the first things that you see there is how to write your own asset configuration. For instance, for a robot, you're going to write an articulation configuration class for that. Now, what is a scene? A scene basically brings all the assets into one place. So even though you have the configuration file for your robot, for your sensor and all of that, you need to bring all of that into a scene. So a scene is a simple configuration class that initializes all the assets in the scene that are needed for the task and for the visualization. So Isaac Lab provide configuration class for defining that schema properties of different assets and scene. Knowledge of USD is still required to understand some available asset on different kind of USD prim. But if you don't have definitely full knowledge of USD, you can definitely take any of the examples right there and then use that to be able to develop your own example. All right, so we'll try to look at what does it look like in terms of code snippet. So for example, 4 assets right here is the ground plane, the lightning, the animal C robot, and the content sensor. So right on the left here is what it looks like for the robot configuration. You can find anything that involves the robot configuration classes in the source folder. So Omni Isaac lab assets. In a lab asset folder, you see a bunch of robot configuration classes right there. So this is for animal. So animal C has the articulation config. So for the articulation config, it has some sub functions inside. One is spawn. Spawn is basically helps you to be able to like put that file of your asset. Like I said, you have your .usf asset, and then you just define some rigid properties. Like for instance, do you want to disable gravity? Do you want to retain acceleration? Some linear damping? What's the maximum velocity you want for this? This is a place whereby you can still kind of manipulate some of the properties in USD for that particular robot that you need. So of course, then you define what the initial state of the robot is. The actuators, we have also different ways of defining actuators. So we have different actuators that you can define for your robot, and that is also on the tutorials. To be able to see how do I define my own actuator, closed loop, different kind of drive systems that you need for your particular robot. So I can imagine if you just have like a very simple what do I call it, like an AMR, like an autonomous mobile robot, and then you just want to define what does the differential drive robot looks like. So this is where you're going to define all of that. And then when you have your robot definition, you come back here. So for us, we already have ground plane and lightning already there for you. So you don't need to define it yourself. So you can see right down here, we have the information for the contact center. So that's the config file. The lightning right here, this is skylight there. For this example, we don't necessarily need the eye scanner, but this was definitely defined because we're trying to do both rough terrain where you need the eye scanner, and then you can separate. You can just put this to none if you're working on flat terrains. So that is also defined in the Omni Isaac Lab task folder for manager-based system. Manager-based example. We also have direct-based example. We'll differentiate between what manager-based and the direct-based actually mean in later terms. So this is the first step that you need: your robot asset file, your other assets that you need. For instance, if you are definitely looking at manipulation and you need a table, you will need a table asset, and then you write a configuration file for this. When you have this configuration file, this helps you to be able to spawn this robot or this asset into the Isaac Sim scene for you. So the next thing you want to look at is I have that scene already defined. What's the next thing I need to do? You need to design your robot learning tasks. So when you say you design your robot learning tasks, means that you design okay, what are my observation? What is my action? What is my randomization? What do I want to randomize? What's my reset function and all of those things? So what's my reward function? What's my termination? So that's what I mean by design your robot learning tasks. So in Isaac Lab, tasks are implemented as environment following the Gymnasium API. I know the last time we had a live stream, someone asked that does Isaac Lab follow Gym API standard? Yes, it does follow Gym API standard. And then we have two different taxing framework that are supported. That's the manager-based and the direct-based, which I'll go into the next one. So when designing your tax, we'll show you how to design that tax, for instance, for the example you're looking at. And then the next thing is to register that environment that you've designed with Gymnasium. Of course, we all know why we need to register environment with Gymnasium. Let me just as we all do know that. But in case we do not, registration is just a way to make that environment accessible and reusable across different learning algorithm and experiments. So if you register with the Gymnasium, all you need is a unique environment name. And with that environment name, you can spawn as many of that environment for any of the learning tasks that you want to do. So I'm just going to take a pause here just to be able to see what questions that we have concerning what we've spoken so far.
This is great. I took our webcams off for a minute so everybody can see the text a little better on the screen.
Okay.
But yeah, and I mentioned this in the chat, but in case anybody missed it, don't worry, these slides will be available. We're going to post them as a reply to the forum post regarding today's live stream. So if you go to the forum announcements for NVIDIA Omniverse, you'll see the thread. I'll post it again towards the end of the chat, but we'll post this file there for everyone's viewing. Really, really well presented, obviously.
Okay.
That's a great questions and comments from all over the world.
Yeah, we have really good questions. This is great.
Okay, can you import your articulation controller from Isaac Sim? I'm wondering what you like, import from where to where? Okay. Okay, if I kind of understand it, let me just assume I understand it. So you have an articulation controller that you've designed in Isaac Sim for your robot to be able to work. How can you use that controller in Isaac Lab? Definitely, it depends on how you define it. If you define it as a Python script, for you to use it in Isaac Sim, or you need to take that Python script to Isaac Lab, because Isaac Lab technically is another way to relate with Isaac Sim using the Python scripting framework. Right. So if you define your articulation controller using Python, it's as good as taking that same script and running it, and that should be able to work well with that same asset in Isaac Sim, since that is how we interact with Isaac Sim. So another question is, how do I get asset from Omniverse Nucleus? So right here is the animal USD file is hosted in the Nucleus directory. So if you're able to access this, then you should be able to access most of the, all you need to do is to provide the USD path file. So if you're able to access the Nucleus directory, with this example, you can definitely access any of the assets in the Nucleus directory. So that's one way to do that. So you can obviously see, for instance, we have the example of the lights. The light right here is from the Nucleus directory. The visual materials are Nucleus directory. So you have other things like maybe you want to add like grass environment. You have all of that, and then you can just navigate through the path for it, and that way you can access that. Okay, so okay.
Well, I see one more question right now. It says, will you show an RL training process using sensor data? And how do we write the policy reward punishment structure?
Okay.
So I think this is something that's upcoming, right? And
upcoming,
also,
yes.
yeah, I'll let you talk about this soon.
Okay. All right. So since that question just came up, I'm just going to continue with the slide, and then hopefully we can ask more question on that. So the question is training process with sensor data. In this particular case, for this animal tax, we're using definitely the sensor data, which is the contact sensor, which is the observation. Like I said, the observation is the position of the position of the base velocity and all of that. Definitely that comes from a particular sensor. If you're actually doing it in real world, you probably have cameras, visual slam, and all of those things to be able to get that information. So all of that is gotten, and the next thing you need to do is to get that information, design the tax for it. So one way we define tax for reinforcement learning, we're going to look at reinforcement learning and imitation learning. One way we define tax in Isaac's lab is what we call the direct workflow. Now, for most people that have used like OpenAI Gym or MuJoCo and all of those other reinforcement learning platform, this would be more similar to what you actually do. So the first thing we do is that in Isaac Sim, you define the tax. Sorry, you define the environment, the asset, or you design the environment. And then in Isaac Lab, you create that scene, which we've already spoken about, which you have your rigid body, your articulation, your sensor. Then the next thing is to define the environment. So the environment will mean you define your observation, action, reward, your command, which is kind of optional, or curriculum, which is kind of optional. Then you define your steps, your environment logic. So your environment or logic involve number one, how do you apply your action? How do you compute signals like done? Is it done? Is it not done? How do you perform reset? How do you perform randomization? So all of this is defined in a particular script. So in direct workflow, one of the benefit of it is like what you see is what you get. Whatever you script yourself is what you actually see your robot doing. It's easy to learn and implement because definitely it's following the conventional way of writing a robot learning task. A single class will handle the entire environment. So a single class will definitely have sub functions like the function for applying actions and doing every of these things. It's suitable for complex logic. The complex logic because sometimes you may not necessarily like I can say that okay, I want to step for 10, like for instance, I want a robot to walk for 10 epochs or 10 steps. And after walking for 10 steps for a quadruped, I want it to do an I5 afterwards. Raise one leg and do an F5 afterwards. Those are different tasks, right? Those are different tasks. And there's a way you can do it, the hierarchical method or different kind of method. So it's not just one policy that does all. So how to be able to implement that, how to be able to like manipulate those kind of logic, especially when it becomes complex, you look at what we call the direct workflow. And all of that environment is then passed into the learning agents, which we will consider later on. The other way of okay. Another thing that I kind of ensure that we kind of have for these office hours is I define what we want to do and then we look at what the code snippet look like. So everything that involves the direct based workflow task is defined inside the lab task direct folder. So for the other one is manager based, it is defined in the management folder. So this is direct workflow, so it's direct folder. So this is just a code snippet or what it looks like in an environment. If you go all the way down here, you see what we call the function called setup scene. So in setup scene, you can spawn your robot, which is your articulation config file. You can define your contact sensor. You can define every other ones that is down here. You can define your apply action function, your get observation, your get reward. So each and every of the robot learning tasks is defined as functions. And then you can define what you want inside that function. So in this case, we said we're looking at the base velocity, the linear velocity, angular velocity, the projected um, um, gravity, the commanded target XYZ position. We have the relative joint position, joint velocity, the height information, the last action. So basically what we saw in the example is what we actually have coded right up here. That's for the observation. And then of course for the action, we have the set joint position target. And that's what we have coded up here. So everything in direct workflow is in a single file and they are all implemented by a single class and you have to implement your own function to be able to get all of those things. Now, the other flip side of the workflow that Isaac Lab provide for us is what we call the manager-based workflow. So what's the difference? So the manager-based workflow breaks down everything into fully reusable sub-modules. It means that after you have designed your robot in Isaac Sim, and then you define your task, your scene in Isaac Lab, you have things what we call event manager, action manager, command manager, reward manager, different managers that handles the tasks that you want to do. So all you need to do for us is that tell us what you want. Like tell me you want this particular observation, your position, you want that, or this is action you want. You don't need to define your step function. You don't need to define the logic. Normally when you have all of those defined, you have to define step. How does the physics work? How does it step? When you apply an action and you want to get the next state, how do you get all of that? All of that needs to be defined. Your reset function needs to be defined in direct based workflow yourself. Your randomization, how you the mathematics behind that needs to be defined. But for management-based workflow, you just tell us the exact thing you want, and then we do the logic for you. So it helps to improve usability, reusability. It means that I can swap out. I can say, okay, I don't want to use velocity observation manager. I want to use a different one. I can easily swap out those sub modules. I can have maybe somebody like say Asari working on the action manager, or someone else, maybe Edma working on the curriculum manager. Different kind of ways of defining things. So it helps for community. Helps to be able to collaborate with different kind of people, because those individual parts can be substituted. So it minimizes risks of logic errors, since you don't have to implement that yourself, and it's faster to implement once a new task is to implement a new task once the learning curve is surpassed. So this is a little bit different from the regular way of defining robot learning tasks, where you have one class define all the functions that you need. This you define, tell us what you want, and then we handle the logic for you. So in that case, this is what it's going to look like. So like I said, all the tasks are defined in Omni Isaac Lab task folder. For manager-based tasks, it's defined in manager-based folder. For direct-based tasks, it's defined in direct-based folder. So for manager-based, one thing you initially see, you just see a bunch of managers. Oh my God, from Isaac Lab, from Omni Isaac Lab .manager, you see a bunch of managers that you have to import. Then right here, you just tell us what the action config is, observation config, the reward function, determination function, and then the logic behind it is not defined by you. Everything is just put together in a scene config, and then we undo the logic for you. So that's what the management-based workflow looks like. Lastly, before I take the next question, we look at the imitation learning. So Isaac Lab doesn't just support just RL, it also supports imitation learning. So imitation learning workflow, majorly the example we have right now works with the management-based workflow. Definitely you can do it for the direct based workflow, just a little bit of change that needs to be done. And of course, many more examples are coming with the next release. And definitely we can have more examples for this. So initially you design your robot in Isaac Sim, same process. You spawn it in Isaac Lab. The only difference right here is that you're now going to collect demonstration instead of just defining reward function and all of those things. You collect demonstration, and we have the functions for you to be able to do that. So if you go to the documentation under teleoperation and imitation learning, you'll be able to see how to do this. So we have an option of using either a mouse or a keyboard to get the information, or to get the demonstration. Or in future release, we have different kind of custom way of getting information. You can use like a VR system or a XR system to be able to get all of that. You split your data into two, and then you have split your data into training, validation, and test set, and then you let your learning agent to learn. One interesting workflow that we're also bringing in Isaac Lab, in commonly release, is what we call the group mimic. So you collect demonstration by either using your mouse to collect this, or maybe using human demonstrator to collect that. How much more can you collect? Like, let's say 10 of that, 100 of that, and that could be interestingly time consuming. So we will be introducing another workflow, what we call group mimic, into the Isaac Lab for it to generate more data. So it takes your 100 of human demonstration, and it generates random. It generates almost like like you can generate up to as many as more data that you can generate, so up to like a thousand scenarios of that same data that you're trying to generate. So for instance, in this example where the robot is trying to lift up this cube, all I need to do is to drag this manipulator all the way down and then pick up that cube every single time, every single way, and then I can have Mimic help me to generate that data, generate more of that data. And of course, we know that the more data you have, the better train your policy is. So that is a very interesting feature that I think everybody should look forward to in the next release of Isaac Lab. All right. Okay. I'm just going to try to see if I can get one question to answer so that we can go ahead with this. Okay.
I see there's a conceptual question around using LLMs with Isaac Lab. Oinda, hold on,
Okay.
pulling
All
it
right.
up. Uh,
Okay.
can I integrate LLM with Isaac Sim? How will it be different from using Isaac Lab? So I can take this one.
Yeah.
In this case, we these are just two different use cases. So integration of an LLM with Isaac Sim, yes, you can. That can be done. But Isaac Lab is more specifically when you want to train a policy or a model around reinforcement learning or imitation learning. Whereas an LLM, if you most likely you are talking about a pre-trained LLM, in that case, you can just write a Python wrapper for it or C++, whatever you're using, and you can just have it communicate. If it's via ROS, you can enable the ROS bridge in Isaac Sim. So that's the first part of your question. Like, yes, there are ways to doing that. As to how it's different from using Isaac Lab is the application itself. So Isaac Lab would be more for when you want to train, let's say, a locomotion policy for a quadruped, or you want to train a pick and place application for a robotic arm or manipulation. That is something where maybe you wouldn't be using an LLM, but using some of the features and functionalities in Isaac Lab.
Okay, thank you, Asa. I think that's good. One thing just to be able to add to that is that you can also definitely incorporate LLM into I mean basically what Asa said is some of the examples in iCloud. So there's a project called Eureka, EUREKA, that you can look up, and that's in it's another way where you can put LLMs as part of the reward function for training your policy. So that's definitely is a project that you can look into, and that should be able to give you more base to be able to use LLMs with Isaac Sim Club. Thank you so much, Asa. Thank you for answering the question. Okay, so straight up, I'm just going to try to run through the rest of the slide. This is quite simple for us to walk through. So you have your environment, and if you can look at what we've been looking at in the environment is that it's defined in a particular class. It's not necessarily defined with like gym or a particular standard. So it's defined with like PyTorch functions. Now, when you have that environment and now you want to use it for any of the tasks, you need to register it with Gymnasium. And we have both for direct based and management based workflow. Yeah, it's quite similar, nothing too much. All you need to do is you give the ID. ID is the final name of the tax that you want, the ID or the name of the tax. So for every of the tax in Isaac Lab starts with Isaac. So Isaac dash velocity dash flat animal seed direct VO. So most of the direct have the direct name. The manager base doesn't have the direct name. That's one way to differentiate between what is the manager based tax and what is direct based tax. Then the entry points, basically you're defining where your environment is defined. The imports the class, then different kind of arguments like if you're using RL games to be able to train, what's the where are you defining your policy, how many, what's the architecture looking like, what's the epoch looking like, your hyperparameters. So all of that is just imputed into this gym.register function, which some of us would have used before if you use Gymnasium, and then that is just used in Isaac Lab for it to register with that. So the next thing, so we've spoken about, you have your file, your input file, you write your configuration for your assets, you spawn your scene, define your tags, either direct base or workflow base. You register it with Gymnasium, which means it is ready to use. Now, an interim between ready to use and running training is what we call the wrap environment. So wrapping environment means that if you want your environment, you want to change the environment you want to change the behavior of the environment without changing the environment itself, you can definitely use different wrappers for that. So for instance, maybe you want to modify the observation or the reward function, or you want to record your training videos. Like as you train, you want to record the videos for that, or you want to enforce some time limits. We have different wrappers for that. Gymnasium offers a whole lot of wrappers, like video wrappers, different kind of wrappers that is right there. You can definitely look into that. But also Isaac Lab provide its own wrappers to be able to convert the environment you created into the expected interface by the learning library. So different learning libraries use different kind of data structure. For instance, as stable baseline use like NumPy, RSLR can use like Touch. So we cannot create for every example or environment you want to create in Isaac Lab, you can create one for NumPy, one for PyTorch, one for different kind of data structure. but we have wrappers to be able to convert whatever you have in that PyTorch environment to whatever interface that your learning library wants. So we have support for like almost like more than like 4 different learning libraries: RSLRL, RL Games, SKRL, Stable Baseline 3, RoboMimic. That's almost like 5 different ways of writing of learning libraries. And also we have documentation, like if you want to design your own learning library, or you want to use a different learning library that is not any of those for you to be able to use, we have that. And so you can just check the wrappers for the one we provide and use that wrapper to be able to use, to be able to duplicate and do what you want. So finally, we'll go into seeing what does the wrap environment definitely look like. So you have all the wrappers for the learning framework are in this folder. So Isaac, Omni Isaac lab tags, UTS wrappers, you have all of that for that. For recording videos by using the Gymnasium wrappers for that. For adding neural libraries, I just put a link right here for you to be able to like see how do I have my own neural library. So code base, you create your Isaac Sim by using gym.make, put the name of the tags, the config, either do you want render mode. I think the render mode will be very familiar to most people using OpenAI Gym or Gymnasium itself. Then you wrap the environment around your learning libraries. Then you can now put every other wrappers that you want. So this is what it looks like. So we have ready to go custom, ready to go wrappers, and then we have you can define your custom based environment wrappers, and information is that for that. So last thing is, okay, I have my environment, I have my robot. How do I train? And that's one question that Asarari has helped us earlier to be able to explain the compute requirement for training. So that is good. We have multiple robot learning framework wrappers that we provided. We mentioned that already. You can implement your own wrappers or additional libraries if desired, but it will require you to write that. We have support for multi-GPU, multi-node support in some RL libraries. RL Isaac Lab can also run various cloud infrastructures using what we call the Isaac Automator. So Isaac Automator helps you to quickly deploy your training on public cloud like AWS, GPC, Azure, and Alibaba Cloud are currently supported. So we have script for training. If you're someone that, okay, I just have a laptop with a NVIDIA GPU and I want to train, we have that training script for that, and we have that for testing also. So this is what it looks like for training. So this for a single GPU when you want to train, and then and this is what it looks like for testing. So this is not necessary for you to look into the code. This is just for you to see the directory that it is. So for our example, we are using RSLRL to train. We have also different train and test script for other training libraries, other robot training libraries. But for the purpose of the example we are looking at for using RSLRL. All right, so finally, I've said finally quite a number of times. So I really hope this will probably be the last finally, but I don't think so. We still have 2 more workflow to look at before we just round up this office hours. The first thing people ask is that, okay, how does Isaac Sim and Isaac Lab relate? And I'm just going to show that using a data workflow. If you followed the reference architecture, you obviously see how both of them relate. But just in how does the data flow? The first thing is that you have your asset in Isaac Sim. Most of the time you try to run your training off screen rendering, which means that you're not necessarily you can definitely run the robot with the GUI running, like train a robot with the GUI running, that's fine, it's just more slower, but you want to also run it headless. And but in any of the case, the asset is in Isaac Sim. Isaac Sim gives access to the observation, which is definitely the state of the robot, position, velocity, gravity, and all of those states. We add noise to it using the event or randomization config. We call it event config in Isaac Lab configuration class. That's how you define your randomization, and that gives you the observation. Now, when you have that observation, all of that is done in Isaac Lab. Now you pass that observation into your policy, and your policy generates an action. This happens in the RL library. So you define your policy, the hyperparameters and all, definitely in Isaac Lab. But the RL libraries is actually what takes that policy for you to be able to train it. Using any of the, like for instance, reinforcement learning, can use TD3, you can use PPO, and any of those algorithms is able to use. So Isaac Sim gives you, the robot, you get the state in Isaac Lab, you pass the state into the policy that generates the action. Now that action can then go back into Isaac Sim, and we perform a physics step. So when you perform the physics step on the asset, it gives you the next state, and then that data just keep flowing that same way, all until the policy is finally trained and you have the trained policy. Now, the interesting part, which is a bit different from the conventional way of doing like robot learning, is the visual based part. Now, when you do the physics step, you also want to render the scene. So if you're doing like visual based area where we are putting visual observation into your observation, then you need the visual aspect of your scene, and that is what is being rendered in Isaac Sim. So that visual aspect coming from a camera is also then passed into the policy and then used to be able to train the policy to generate the action. So this is just a simple way in which data flows from Isaac Sim to Isaac Lab. For the example we're looking at, this was trained on a desktop GPU of RTX 4090. The CPU is just Intel 13th generation. We trained this on 4,000 training environments. 300 steps was just trained for 5 minutes for the particular task that we're looking at, and 1,500 steps for just 22 minutes. And that is using just a 3-layer multi-layer perceptron with 128 neurons, and that's all about it. And yeah, we have our robot working. So this is working after 4 minutes, training for 4 minutes, and then the robot is working. And of course, you can train for more longer hours just to ensure that your policy is you just train your policy better. And the blue line is showing what it looks like after 300 steps. The pink line is showing what it looks like after 1,500 steps. So this is just one of the reward function. This is for the linear velocity that's been tracked. That's the XY velocity, and this is the rotational velocity that's been tracked. And also we can see that even with just a very simple basic, okay, I don't want to call it basic GPU, but within the laptop GPU, you can train a quadruped to work in 20 minutes, and that is a huge step from training from like weeks to just in days. Finally, we'll look into the sim to real workflow, because one of the questions people ask is that, okay, now I'm able to train a simulation. How do I bring it to the real world? I really want to engage everybody and answer question, but I just want to finish this part and then I'll be able to go back to the question. Is that okay? Because I know that time.
Yeah,
Okay,
yes, yeah, of course.
okay.
Take your time.
All right, good. All right. So, like, I know a lot of us want to do things in the real world. Of course, we don't want to start in the real world because you don't want to break your robot, but you want to start in simulation. But you also want to guarantee that what I have in simulation will actually work in the real world, and that's what sim to real is. It's a guarantee that whatsoever thing I design in the simulation world, if I train it in the simulation world, it can transfer to the real world. And yes, we are saying that we have tools for you to be able to do that. And one of the interesting part is for you to be able to do domain randomization, which is the key part in sim to real. Domain randomization means that you have your scene and you can randomize it. You can add noise, because in the real world there is noise. The fact that you tell a robot to move forward, it might not necessarily move forward in the real world. It might move with a tangent of 15 degrees, and all of that needs to be modeled into the simulation. So domain randomization is a key way, which I've been calling event configuration file or randomization in Isaac Lab. So in the real world, in sim to real, this is assumed that you've trained the animal in Isaac Lab and you have your trained model, which you can get in .pytorch or .onnx or Onyx file extension. So first thing that you have your robot, your hardware, like your real robot that has a sensor. For instance, you buy an animal C robot. And then the first thing you need is your state estimator, because that's how you get your observation. So there are different state estimator you can use. For instance, for animal, any robotics has their own custom estimator for us to be able to get that. For Boston Dynamics Sport, they have their state API for you to be able to get that state estimator. We also have like different tools like NVIDIA Isaac Perceptor, which is using Visual Slam. Sorry, I guess I'm right on that. Okay, Visual Slam for you to be able to like get your state from your robot, or different Isaac Ross packages, that you can use, different packages that you can use. Maybe you're using LiDAR or you're using any of those system that any of those sensors to be able to get your state. So when you get your state, you get your observation out of that. Now that observation is then passed into your train model, and then you get your action. Now, the action that you get really from your RL policy or from your imitation learning policy can either be the direct action that you can put on your robot or a commanded action. So in this case, we have a joint position. Now, the joint position is then passed through what we call the action controller. If you're using a AMR, you have, let's say, the velocity and the angular velocity from the robot. Now that needs to be passed into like a PID controller for you to actually use on your robot. So that's why there's a bridge between what you get from your policy and what you get from your action. And of course, the commanded action is passed back into the observation extractor and then passed into the model. Now, all of this can just be a Python script that can be coded for you to be able to do this. And with this, you should be able to transfer what you have from your sim to your real world. And someone's like, "Oh, is it that simple?" Okay, yes. It's this is a sample real sim to real workflow. There are more complicated things that definitely can come up to it, but this definitely is what was used in developing this example. So this is Boston Dynamics spot robot that was trained in Isaac Lab. This was trained for less than 4 hours for you to be able to train this, and the exact policy that was running in simulation was transferred to the real robot. So this is Spot working in one of our NVIDIA campus right here in HQ. And that same policy was transferred without any change in the policy. So I just trained the simulation and I went into the lab, deployed it on Jetson Orin. So that's Jetson Orin right there on Spot. And then that was used directly to be able to make Spots to be able to work. And it's very interestingly versatile. I didn't experience so much difficulty in doing that. So that previous workflow that I shared was exactly what was technically used, except for the fact that the state estimator was Boston Dynamics state estimator. They have the joint API for you to be able to do the action controller for that. So this is an interesting application of using Isaac Lab to perform sim-to-real application. This is also explaining a blog that the link can be shared for us to see how exactly is this done step by step. And of course, if you want to do sim-to-real, you have to write your own script for running it on the real robot. The reason is because we have different kind of tons of real robot, and some of them require different kind of state estimator or action controller and all of those things. And so what we provide is a train policy from Isaac Lab and the environment config from Isaac Lab, and then that you can use for your real robot. All right. So that's the end really of the office hours today. I'll switch back to the question, but I just want to point out that we have documentation, and Isaac Lab documentation is actually very good for us to be able to follow. We have tutorials on that documentation. This reference architecture is right on the documentation. And we have different workflow guide. How do I add a new sensor? How do I, get images from different multiple cameras? How do I do actuators? Some of the questions that we asked previously was like, how do I design my own actuator? There's the documentation for actuators on that, on Isaac Lab. How do I customize my own model? How do I do all of those things? All of that is spelled out in the documentation, but we'll just go straight to the questions and just ask them. I hope we're able to do justice to some of the workflow on how to be able to develop with Isaac Lab from the initial point of getting your asset down to training. Thank you all for listening, and I think we'll go to the questions right now.
That was awesome. Very, very cool. I mean, I'm blown away by all the questions and comments coming in. Asari's been keeping up with them as best she can. This is fantastic, though. I'm going to post. So I posted a little earlier. I started a thread because I see so many great questions and comments and people talking to each other and discussing their projects. I think it would be really valuable for the community to actually continue the conversation on this topic. So I've created a thread on the Omniverse Discord server. I just posted the link. If you're not a member of the Discord server, it's super easy. Discord is very easy to use also. Just go to discord.gg/NVIDIA Omniverse to join the server. And then you can use that link to actually give your feedback, ask your questions, comments. I'm sure we can get our colleagues here to jump in the Discord and chat with you all too. But also mainly it would be great for the community to chat with each other and help each other. I see some great contributions in the chat, including from Shane Reitz, who Shane also just made a great post on LinkedIn today. I'll post that link in the chat also regarding Python and Omniverse, the different ways you can leverage Python. So anyway, thanks for Shane for helping out. And I see Papa Chuck on here from the community helping out also, many others. So thank you all for helping expand the team here at NVIDIA with your own knowledge. There are some great resources on the screen here. We are going to, as I said earlier, we're going to share this slide deck. We're going to put it in the forum post where we announce today's live stream as a reply to that. So you'll be able to grab it there. I think I should be able to upload it to that Discord post I just shared a second ago also. So you'll be able to get one or two places. But the forums are a great place to discuss Isaac Sim in general. But I think, sorry, aren't we using GitLab to actually discuss Isaac Lab? GitHub?
Yes.
Sorry?
So I'll share a link again to the GitHub for Isaac Lab. That's a good place for the more detailed questions that you can't just, Google and get an answer. That's the place where if you have more like log files, errors, any messages that you want to share with us, your trained models or whatever, that's where you should be doing all of that. And also it's just, many people have already started asking their questions and getting solutions on there. You might just find someone has already faced the same issue you're running into. So let me go ahead and share that link again in the chat right now.
Perfect. Thank you for that. Really, really amazing information. Lots of kudos here. I'll just put the last one I just saw. Great presentation of information. Great demo. And I think everybody was able to ask their questions here. I'm sure we didn't get all the answers, but again, follow the recommendations we just gave out either on the GitHub or in the Discord server. And we'll post the deck in the forum and also Discord server. The next session is going to be actually, the next live stream is actually going to be on December 4th on industrial automation. Very special announcement on a big guest who's coming to that one. So we'll release that as soon as possible. But in terms of Isaac Lab, which is probably what Samantha may have been, or Samarth, I'm sorry, may have been asking, we're gonna add that to the calendar as soon as possible. Right now, we're just gonna finalize the schedule for that. But obviously, such great demand and interest from the community. So that's super helpful when we try to align the right people here on our side to give presentations like today. So we will keep you updated. The best place to find out our upcoming live streams is actually our Add Event calendar. I'm going to post that here. That's where you can see upcoming live streams. And we basically fill in the details as we approach that date. So sometimes you might see kind of a high level topic for an upcoming live stream, and then we'll narrow down that topic. Very easy to add to your calendar there. If you remember the Discord server, we also post them in the events area in the top left. Thank you all for joining us today, and thank you for our wonderful presenters. Sorry, I can't thank you enough for presenting such great information, such great order and examples.
Thanks, everyone.
Okay, thanks, Leah. Thanks, everyone.
Yeah,
and thank you, Edma, for being the host of this.
Oh, of course.
Absolutely.
That's the easy part. That's the easy part. Thank you all for joining us. We had hundreds of people watching today, so thank you so much. And it's a real good testament for the power of the community on leveraging this technology, and it really helps us enable us to bring more of these events to you. So thank you for participating. Let's continue the chat on Discord and on the GitHub. And we will see you next time. Thank you all for joining us today. I hope you have a great rest of the week. Thank you, everybody.
Thank you.
Thanks, everyone.